everybody. I'm Sean Stepinski at Refrigeration Sales. Today I wanted to show you how to use the Firelight Pro as a manometer. A lot of guys use this as a combustion analyzer, but one of the features is it can measure pressure. So I'm going to show you today how to use this to check things like total static pressure, which is one of the more important readings that we take. When we take total static pressure, what we're looking for is the total resistance value in the ducting system on the supply side and the return side. When you buy a piece of equipment like this furnace comes set up and it says it is certified to give you a certain amount of airflow at a certain static pressure. If you exceed that static pressure, your airflow is compromised. Or in other words, airflow is directly proportionate to whatever the static pressure is in the ductwork. So we want to keep the static pressure under the maximal allowable setting that is listed on the unit. The guys always go and look at the name tags. It'll give you the model number, the serial number, temperature rise, gas pressure. But one thing that is also listed on that nameplate is the maximum certified external static pressure. On the nameplate of the unit, you will find important information like the model number, serial number, voltage, gas pressure, temperature rise, things like that. But one of the things that is listed on this piece of equipment, you can see right here, maximum external static pressure. That is the maximum allowable external static pressure for the unit. That is what it's certified against. If you stay underneath that, which means you'll get all the airflow delivery that the equipment is rated for. If you go over that, the airflow becomes compromised. So you always want to stay under the maximum level. Typically residentially, we're dealing with 0.5 inches of water column as a maximum level. That is typically in the cooling mode. In the heating mode, furnaces are rated without an air conditioning coil because there's no guarantee that the furnace has air conditioning. It could be one without an A coil. So furnaces by themselves are typically rated much lower for airflow. So in the heating mode, they might be rated at 0.15, 0.25 inches of water column, which is considerably less than the maximal level. So if you're in the heating mode, checking your total external static pressure, you always want to stay under what the maximum level is, because if you're at the maximum when you're in the heating mode, when you go to air conditioning mode, you're certainly going to exceed that. And at that point, the airflow is going to be compromised considerably. Now, when you're checking your static pressure being defined by what we're talking about is the pressure that's exerted on all the walls of the duct all the way around equally. There's different types of pressure for this particular portion. We're not going to go into all the pressures because there is velocity pressure, total pressure, things like that. But specifically today, I want to talk about static pressure or the resistance that's in that duct system. And one way you can do that is by making two holes into the system. What we want to know is we want to evaluate the entire system, the supply side and the return side, all at one time. So you have to punch two holes into the system in order to get those numbers. One hole you have to have is between the furnace and the first piece of resistance. Typically, that first piece of resistance is an A coil if you have air conditioning. So you actually have to be between the furnace and the coil. So that is the first hole that you would have to make. The second hole you would have to make is between the filter and the furnace. You have to be between these two and not on this side. So you have to be between the filter and the furnace. A lot of times you can access that right through the blower door as long as you have a good seal, on the blower door itself. When accessing the reading, I recommend you use something like this. This is what we refer to as a static probe. If you look at it, it is bent at 90 degrees. It is actually welded shut on the end, and it has holes on the side. When you are checking static pressure, since it is the pressure that is exerted on all the walls of the duct all the way around, your inlet, your sensing probe inlet, has to be 90 degrees to the airflow. So if the airflow is going this way, your inlet sensing probe is this way. But so when you look at these, when you put this into the ductwork and your supply air is going this way, you point it in the direction of the airflow, you'll see that the sensing probes are 90 degrees to the airflow. Airflow is going this way. Inlet sensing probe is 90 degrees to the airflow. So I recommend you use something like this because if you use a regular probe that has a hole in the end, when you stick it into the duct, if it moves up or down or left or right, it will change your readings considerably. So if you to be as accurate as possible, use something like this as a static probe. What I did is I have the Firelight Pro running as a manometer. I have two hoses. I'm running it as a dual manometer. So I take my static probes and I attach it to the end of the hoses. And before I insert my probes into the duct system, I want to zero out the meter. And one way I can zero out the meter here is I scroll down and then I hit the enter button and it should zero the meter out. So the first reading we're going to take is I'm going to take the static probe, I'm going to put it between the coil and the furnace, and I'm going to point this in the direction of the airflow. What I want to know with that reading, that is a positive reading. What I want to know is when that air comes out of that furnace, how difficult is it for to push the air through the coil, up the duct, turn left, right, down the extended plenum system, out the orifices or the registers. How much pressure is built up right here? How hard is it for that blower motor to push that air? So that's the first reading we need. The second reading we need is on the return side. And the same thing is, we want to take this probe and we bring it down here. And I'm going to use the blower door section right here. So when I put that in, the second reading, and this is a negative reading because it is on the return side, it is the suction side. So what I want to know on this particular side is the air that's being drawn across. How hard is it for the blower motor to pull that air across the filter, all the way down the grills, the ductwork? How difficult is it to pull that air? So once I have those two numbers, basically what happens is this is a negative number, this is a positive number. When you take the total or the sum of the external static pressure, you add those numbers up. In this particular case, by using the Firite Pro, it does the math for you if you're bad at numbers. But you could do it one at a time. When you take this number would be a positive number. This number down here will be a negative number. But when you take the sum or the total of the two, you forget about it being positive and negative. Just add the two numbers up, and that will give you your total. In this particular case, the meter does that for me. So in this particular system, I am running right now a total static pressure in ESP at 0.55 inches of water column, which is just above, slightly just above what our maximum allowable level is for this furnace. I am running continuous fan right now. On this particular piece of equipment, the continuous fan mode happens to be the low heating speed, so I am actually running too high. There is too much resistance in this duct system. Remember what I said earlier is when you're in the heating, you want that number to be a little bit lower because the 0.5 inches of water column that they typically rate for residential equipment is a cooling number for maximum levels. Now what I wanted to show you was a very common mistake that technicians make out in the field when measuring total static pressure. I've seen some of the most experienced guys make this mistake, and it can give you a false positive reading. So I want to show you how to avoid that. One thing that guys tend to do is, this is my actual static pressure right now. And again, I'm taking my readings between the coil and the furnace. Knock that thing out there. Between the coil and the furnace, and between the filter and the furnace. And that is the correct way to do that. But what guys tend to do out in the field is they tend to go to the easier locations. They tend to be on the outlet side of the coil up here in the plenum area, and then they tend to take their other probe and be in the return air drop area. So they're actually not taking into consideration the resistance value of the filter and the coil. Now that same system that I was just running at, that I was 0.55 or 5.2, I don't remember exactly what it was, but you'll see now with these new readings, not including the coil or the filter, I'm running a 0.24. So that's pretty low. That's a pretty good number for heating. It's really low, but it's a false positive reading because that's not accurate because I am not taking into consideration this coil or the filter. Now, I have put over here, since this is a testing facility, I have put a damper in here. So what I'm going to do is simulate some shrunken return duct, high resistance in the return duct. So I wanted to show you what would happen if I turn this and I block some of the air off. Okay. I shut down some of the return air. So now we have the technician came out. He accessed in the wrong testing locations. He is on the plenum area, he is in the return air drop, and then he reads his meter. His meter says 0.50 inches of water column, which looks like a pretty good number. He comes over here to the name tag of the unit and says, that is normal. I am under or I'm right at the maximum level, so I have a good duct system. But that's not true. That is an actual false positive reading because he did not take into consideration the coil or the filter. That what looks like a good number right now, in essence, is a very bad number. It's a very high static pressure. If he was to actually put his probes in the correct location, and again, between the coil and the furnace, and between the filter and the furnace, you will see my actual static pressure is not 0.24, 0.23. My actual ESP, external static pressure for this piece of equipment is 0.69, almost 0.7 inches. So it's way higher than what the allowable level is. Now when you have a piece of equipment like this, keeping in mind that 0.5 is a cooling number. I'm running on continuous fan, which happens to be on this piece of equipment the low heating speed. So when I went to cooling, I could very easily be running at 1 inches of static pressure. And as soon as that static pressure goes up, airflow is compromised. Think of it in the sense that airflow is directly proportionate to whatever the static pressure is. Higher the static pressure, the less airflow. The lower the static pressure, the more airflow. Now, a lot of guys will say to me, I understand that on a lot of applications, you have a case coil sitting directly on top of the furnace. So, although that's a testing area and I set it up so we can test that there is separation between the coil and the outlet of the furnace, I realize that is not always the case. A lot of times you will have a coil setting directly on top of the furnace. When you run into those cases, one good place to get the reading between the coil and the furnace is actually the back side of the furnace. A lot of times I can tap the back of the furnace up at the top area, and I can actually get the probe and tap it in like this. So then the probe will actually sit here, and since I'm looking for pressure that's inside the cabinet, that actually works fairly well. You don't want to be on the sides, because on the sides there's typically baffles, and they could run all the way up the side of the furnace. They are to keep the heat on the outside chambers of the heat exchanger, and they can give you some very false readings that way. But as long as you stay close to the top and don't drill in really far, you can easily tap the back of the furnace like this and get your static probe in there, something like that. Getting familiar with checking pressure drops, static pressure, things like that, you can learn a lot about the system. One thing I wanted to show you real quick as we start winding down here is, you can check your static pressure, your total static pressure, but you can also, since you have a couple holes here across the coil, I can tell you what the pressure drop across the coil is too, and it's pretty easy to do. And again, I do it almost the same way. I take the two hoses off my meter, I attach my static probes, I zero the meter out by scrolling down, hitting enter. Do that one more time. Okay. So I take one of the probes, I stick it in between the furnace and the coil, and then the other probe is on the outlet of the coil. And I am reading a pressure drop across this coil of 0.12, 0.13 inches of water column. And then you can compare that to a lot of product data. I would say most coils run somewhere right around, depending if they're wet or dry, when they're clean, they run around 1.5, 0.2, 0.25, something like that, depending if they're wet or if they are dry. But you can compare that to product data. But when you start seeing really huge numbers, 0.4, 0.5, 0.6, there's a pretty good indication that that coil is probably plugged. And a good indication of that's always if you see a lot of bad filters, dirty wheels, chances are the coil is probably dirty also. I can also take the same setup, and you have to be careful with filters. Filters can have a high pressure drop across them too. High pressure drop filters are typically never a good idea. We see that a lot because homeowners tend to go out and buy filters they hear about on TV or something like that, and you can get a very high pressure drop across them. Some of them work to some degree, but very high restrictive filters are typically not a very good idea. And again, I take my two probes and I put one between the filter and the furnace, and the other one's across the filter. So I'm going to have one on this side of the filter, the inlet, and the other side of the filter where the inlet of the blower motor is. You can see my pressure drop for this filter is 0.17, which is a little bit restrictive. But you got to watch these really high restrictive ones, especially the 1-inch filters. Filters like this that have a high value of picking up, but they're only 1 inch thick. It's very hard to get air through those filters. So those can be really bad and can be damaging to a system. Once you have your total static pressure, although you can evaluate your entire duct system by knowing the resistance value, you can also determine how much airflow you're actually getting. And that's actually a good number to know because a lot of guys, they assume a certain amount. Just because it has a blower drive saying 800 CFM, don't mean you get 800 CFM. Like I mentioned in the beginning, that only means you're getting that if you have the right static pressure. So one thing you can do, once you have your static pressure, you can go to the manufacturing specifications. And most manufacturers will give you a fan curve. It is air performance or air delivery based on static pressure. For this example, it looks something like this. I have this furnace right here, this 06012. That's the furnace we've been working on. It means it's 60,000 BTUs, and it means it is a 1,200 CFM drive, so a 3-ton drive. So you can see this. It has my blower speeds right here, high, medium, low, and low. Across the top is my static pressure, 0.1, 0.2, 0.3, 0.4, 0.5. So what I do is say I'm on high speed, I have this unit, I come straight across to 0.5, is 1,200 CFM. Now, if my static pressure was actually moving up this way, and my static pressure was 0.8, I come all the way across here. Now I got a unit that is operating with 935 CFM instead of 1,200. And a lot of times, you'll see static pressure about 1 inch. That's clear off this chart. And when it becomes off the chart at 0.9, 1 inch, you might be moving 800 CFMs on a 3-ton drive. So how well does an air conditioning unit operate off of 800 CFMs when it's a 3-ton air conditioner? When you are done with your testing, I always recommend to all the guys, you want to put plugs back into all your holes. We're trying to be professionals. You don't want to be covering things up with tape and caulking and things like that. You can buy plugs just about anywhere and make sure all your holes are plugged back up. Make sure they are sealed so it is a quality testing, and it's a quality job that is done. And I also recommend, when you go out, it's one of those measurements that should be taken all the time. When you look at the nameplate, if the manufacturer went through the effort of stamping it on that plate, it's pretty important to check. You should be checking the gas pressure, the temperature rise, the voltage, and doing a complete analysis on the efficiency, including combustion testing, so you know that the equipment is safe in operation and operating properly. Know that your CO is correct. Know that your O2 is correct, and your combustion efficiency. I recommend that when you are done doing all that, you document all that, or if you're using something like the FireRite Pro with the printer, you can print that information off, staple it to a ticket. So later down the road, when you leave there, everybody knows exactly how that piece of equipment was left and the operation it was in when you walked out the door. So for more information on airflow testing, static pressure, combustion chaining, check with your local distributor and trading agencies.